podcast is brought to you by LMU Munich.
Let me join everyone else in thanking the organizers for this great conference and also for the chance to speak here. Can that be fixed? Okay, good. So I want to talk to you about class R. It's a certain set of 3D n equals 2 gauge theories that I defined in work with Davide Gaiotto and Sergei Gukov. More precisely, I should say that it's really a set of infrared SCFTs. But all of the SCFTs in this set are defined by ultraviolet Lagrangians that look like abelian Chern-Simons matter theories. The UV Lagrangians are constructed axiomatically in a way that I'll explain. And, well, they're mainly standard abelian Chern-Simons matter theories, but they have a slight exotic feature in that their superpotential couplings may contain non-perturbative or monopole operators. While all the theories have these abelian UV descriptions, they may have non-abelian descriptions as well, which could lead to some very interesting dualities and could make this class of theories actually quite huge. I'll say a little bit more about that later. The main reason we defined this class in the first place is because it happens to contain the effective field theories of M5 branes wrapped on 3 manifolds. In particular, if one takes KM5 branes on 3 manifold cross R3 in terms of effective field theory with a topological twist on M, one should get a 3D n equals 2 theory, TK of M, that has some infrared SCFT description. Very roughly, the axioms of class R, the combinatorics that build these UV Lagrangians, mimic the combinatorial construction of SLKC connections on a manifold M starting from a triangulation of M and SLKC connections on tetrahedron building blocks. And I will try to say a little bit about that. Given the relation between 3 manifolds and 3D SCFTs, one can then try to study a whole host of new relations between geometry on M and physics in T of M. So I want to talk about some of the past years' progress on these theories on class R and say a little bit about what's to come. Let me start then with the definition of this class. Again, it's axiomatic. The idea is to just follow a few simple steps. So step 1 to define a class R theory is to form a product of free chiral theories T delta. So each of these T deltas contains an n equals 2 chiral multiplet. It's got a U1 flavor symmetry, and we turn on a background gauge field for that flavor symmetry with -1/2 Chern-Simons coupling, which is necessary to cancel background parity anomaly. Altogether, the tensor product of n of these free chiral theories obviously has flavor symmetry U1 to the n. At least, I should say, the abelian part of the flavor symmetry group, the maximal abelian group, is U1 to the n. And I'll keep track of that through the next steps. So part 2 involves 3 moves that all preserve the U1 to the n flavor symmetry. So first, we can simply redefine the flavor currents. We rotate the flavor symmetry by a linear transformation in GLNZ. Second, we can start adding background Chern-Simons couplings to the theory. Classically, the Chern-Simons term involves a symmetric matrix K, and those are the background flavor gauge fields, and the supersymmetric extension is written over on the right. And the third bit is to gauge one of the U1s in the flavor symmetry group But when we do that in 3 dimensions, we always gain a new topological flavor symmetry. So the total flavor symmetry is conserved. And there's an Fi coupling between the background gauge field for the topological symmetry and the one that's been gauged. So again, I've been emphasizing this. These all preserve the rank of the flavor group. And step 3, at the end of the day, is to add some operators to a superpotential in order to break some of the U1s. And these operators may have to be non-perturbative. If, for example, we want to break a topological U1, we should stick a monopole operator in the superpotential. You always have to check rather carefully that the desired monopole operators exist if you want to do such a thing. A really fun observation, and in fact a very useful observation, is that this axiomatic construction of theories matches symplectic actions on a vector space. The operation of forming a product of free chiral theories is constructing R to the 2n as n copies of R2, and it's got a canonical symplectic form involving n positions x and n momenta p. Then in step 2, the 3 moves I described are simply symplectic transformations on R to the 2n. The first one is a linear transformation on positions and the conjugate transformation on momenta. The second one adds some position to the momenta, and the third one switches a pair of position and momentum variables. In fact, these 3 moves not only generate a symplectic action on R to the 2n, they generate a symplectic action on the 3D gauge theories. And this is something Witten defined and discussed in 2003. The really non-trivial statement here is that the relations in the symplectic group actually hold at the level of gauge theories. For example, if we perform a gauging twice, so we gauge a U1, we get a new topological flavor symmetry, and then we gauge the topological flavor symmetry, that's the same as not gauging at all. Finally, the breaking of U1s is a symplectic reduction. In R to the 2n, it means fixing one of the position coordinates and quotienting out in the direction of the conjugate momentum. So because there's this exact relation between the axioms used to construct theories of class R and symplectic transformations, we can encode the data of a class R theory in a single big symplectic matrix in SP2NZ. N is the number of chirals we've started with, and I should say that some of the rows of this matrix have to be marked because at the end of the day we do symplectic reduction. We break the U1s corresponding to some of them. Here's a very simple example. Let's take that matrix. It's got symplectic rank 2, so it means that we start with just a single chiral. We break the matrix up into generators, and the T generator says that we add Chern-Simons level 1 to the theory T delta. The S generator says that we gauge the flavor symmetry, and altogether we get a theory T delta tilde, which is a dynamical U1 Chern-Simons matter theory at level 1/2 coupled to a chiral. Now, in 3 dimensions, there are a ton of mirror symmetries relating UV Lagrangians that flow to the same infrared superconformal theory. We should quotient out by these mirror symmetries in class R. A very simple example, in fact a very fundamental example of mirror symmetry is in fact between the theories T delta and T delta tilde that I just discussed. Another fundamental example involves the XYZ model. It's a theory of 3 chiral multiplets, 3 chiral fields that are coupled by a cubic superpotential, and NF equals 1 SQED. It turns out that, well, so we impose mirror symmetry such as this in class R, but it turns out, and I think one can make a conjecture, that this is really all we need. Any 2 UV Lagrangians that we construct with the axioms that flow to the same infrared SCFT can be related by repeated applications of these 2 moves. And again, this is conjectural, there's good evidence for it, and I think it would be really interesting to investigate it a bit further. So that's class R. It's axiomatic Lagrangians modulo mirror symmetry. As a note, there could be lots of abelian, non-abelian mirror symmetries that give Lagrangians that aren't constructed this way. So class R could really be huge. And it would, again, be really interesting to see how big it really is. In Yamazaki's talk, there were 3D theories associated to three manifolds that started out being non-abelian, and that could give, well, that could be one of many examples where these abelian theories actually have non-abelian descriptions. Now, why do we care? Since we've constructed the theory systematically, it means we can construct things like partition functions systematically. And the precise mapping between steps 1, 2, 3 and actions on partition functions depends on which space we compute the partition functions. If we take some curved compact spaces like the ellipsoid or S2 cross S1, which gives the 3D supersymmetric index, things like the S elements of the symplectic group, switching position and momentum, or gauging in the theory, correspond to doing Fourier transform on these partition functions. So we get a slightly new interpretation of things that have already been defined, and we also get a rather cool new construction of a more fundamental partition function of these 3D theories on a twisted cigar on D2 cross S1. And these will be discussed in some upcoming work with Chris Beam and Sara Paschetti. But the reason they're very cool is because all the other partition functions here can be constructed out of them. Basically, one takes the norm squared of these cigar partition functions, which we call holomorphic blocks. And depending on exactly how the norm squared is defined, one gets either the index or the S3B partition function. Fortunately, that's all the time I have to say. Well, that's all I can say about that. Along with partition functions, we get systematic constructions of word identities. These are the line operators or line defects that Davide mentioned in his talk. But the real reason we care about class R is, again, that it contains theories of three manifolds. So being a little bit more precise about that, if we want to think about M5 branes, we should put them in a geometry that looks like T star of M cross R3 in M theory. Or since we're interested in the field theory limit at the end of the day anyway, we can put the AK-1 to 0 theory on M cross R3, but then we have to do a partial topological twist on M to preserve supersymmetry. Either way, we get an effective n equals 2 theory on R3. To understand why these n equals 2 theories are in class R requires two observations. The first is that the low energy behavior of these putative class R theories is governed by flat, complex SLKC connections on M. It's a statement related to many recent works in these 3D dualities. The second observation is something I already mentioned, which is that given an ideal triangulation, and I mean topological ideal triangulation of M, SLKC connections on the full manifold are glued together from tetrahedra using exactly the same symplectic combinatorics that define theories of class R. So given a number of 5 branes, a manifold, and a triangulation, we can immediately write down a symplectic matrix with distinguished rows and then simply define a UV Lagrangian for a class R theory. Let me give you a little flavor of how this works. So here's the building block of 3 manifolds, a tetrahedron. And I will first talk about the SL2 case, which is what we used in the work with Gayotto and Gukov. The tetrahedron combinatorially gets a few labels on its edges, which have something to do with flat SL2C connections. But these are positions and momenta, right? So there's an x and a p, and they're equal on opposite edges, and the sum around any vertex is 1. And this combinatorially decorated tetrahedron gets associated to the theory of a free chiral, T delta. If we happen to rotate the labeling, then instead of getting T delta, we get T delta tilde, this not a free chiral, but a dynamical U1 theory coupled to a chiral, But this is exactly one of the fundamental examples of mirror symmetry. So because of that mirror symmetry, it actually makes no difference how you orient or rotate or label the tetrahedra. Now, to build a complete three-manifold M, we have to start with a collection of n tetrahedra and start gluing them together. The gluing defines a symplectic matrix. The basic idea is that, well, so it's a 2n by 2n symplectic matrix where n is the number of tetrahedra involved. The top rows of this matrix, the top n rows, correspond to U1 flavor symmetries in the theory we want to end up with. Some of the rows come from internal edges that are created during the gluing. For example, up on top, there are three edges that get glued together with some parameters x1, x2, x3, and that constraint coming from the edge appears as one of the rows of this matrix. These are the glued edges correspond to U1 flavor symmetries that we have to break with superpotential terms. There are also a bunch of rows corresponding to U1s that we want to keep. And in the three-manifold, these U1s that we want to keep have to do with boundaries that are left over or defects in the three-manifold. At the end of the day, we do symplectic reduction, or we break the green U1 symmetries, and we get the theory of class R. And is the basic idea of how these are constructed. As a side note, if we change the triangulation we used to build the three-manifold M, any two changes are related by a sequence of so-called 2-3 moves that look like this. So 3 tetrahedra glued along an edge are recombined into 2 tetrahedra glued along a face, and this is just the statement of XYZ and SQED mirror symmetry. Because of that, the construction of the theories T of M is triangulation independent. So that was the story for SL2 that was worked out with Gayotto and Gukov. For SLK, the story has been worked out in a mathematical physics collaboration with Sasha Goncharov and some physics colleagues, Maxime Gabella, Masahito Yamazaki, and Dan Shi. I want to mention just one fact about the SLK world. Again, one triangulates the manifold into tetrahedra, but the SLK tetrahedra are bigger. The intuitive thing I can say about them is that they can be broken up into roughly k cubed little SL2 tetrahedra. That means that the theory associated to an SLK tetrahedron should roughly consist of n cubed chiral multiplets. They do have some extra superpotential couplings, and there are some gauging. It's not a free theory of k cubed chiral multiplets. But at least naively, it looks like if we crank up k, the degrees of freedom of just the fundamental SLK tetrahedron theory have to scale like k cubed. And that's in rather beautiful agreement with the expectation from supergravity that for M5 brains wrapped on a 3-manifold, the degrees of freedom, as the number of M5 brains grow, the degrees of freedom grow cubically. It's a rather new statement of large N duality. Usually, in these dualities, there's a gauge group, such as SUN or SUK here. And that's what grows. In these abelian descriptions, the gauge group is always abelian, and it doesn't really matter. The fundamental matter just gets bigger and bigger. Let me conclude with 2 of the basic physics geometry correspondences coming from these theories of 5 brains wrapped on 3 manifolds. The first kind of classical one is that at low energies, the vacua of a theory Tk of M that's been compactified in a circle have to match the flat SLKC connections on M itself. And so this is a precise statement of the rough statement of the rough statement I made earlier in the talk. If you actually want SLKC complex connections, you have to compactify in a circle. That's a low energy statement. If we want to test more about the quantum structure of the theory, we should compute partition functions. And really, one can compute a partition function in the 2-0 theory on M cross R3 or M cross a compact space. And that can then be reduced either to M or to the non-topological space. But the basic idea is that whatever you do, any partition function you compute for T of M is related to some version of analytically continued SUK Chern-Simons theory. And exactly what analytic continuation you pick depends on what curved space you are compactifying on. The ellipsoid corresponds to some version of SLKR Chern-Simons. The ellipsoid corresponds to that. The index corresponds to what I'll call full SL2C Chern-Simons, meaning it has both holomorphic and non-holomorphic sectors. And the holomorphic blocks, which I mentioned earlier, are again most fundamental also from the perspective of Chern-Simons theory. And the gauge theory side, they're labeled by vacua at the end of the cigar. Since the space is non-compact, one has to fix a boundary condition. And in the Chern-Simons side, one gets building blocks of analytic continuation that you get Chern-Simons path integrals that are labeled by classical critical points, by flat complex connections. I should say that this relation between partition functions of T of M and Chern-Simons theory is very much analogous to the 4D 2D relation that was discovered a few years ago in papers by Gayoto, Mornaitsky, and then AGT. There we have M5 branes on a surface C that produces a 4D SCFT, T of C. And if one computes partition functions on one side, one gets Liouville or Toda correlators on the other. That is basically all I can say now. This is a sampling of the relations that come out of these three manifold theories and more generally theories of class R. There's a lot more to do, and hopefully there will be a lot more progress soon. But for now, thank you for listening.
Thank you. A few questions before the lunch break. Ina?
When you consider high rank, is there more data in the so you said you have these larger tetrahedra?
Yes.
Is there more data required to glue them than in the rank 2 case? Really?
Yes, but the data looks the same. So one also defines a symplectic matrix. It just happens to be a much, much bigger symplectic matrix.
So knowing the SU2 case is not enough to get the SUN?
No.